Many years of designing and constructing drilling platforms in the Gulf, J. Ray McDermott and Company, Incorporated, has faced multitudes of fascinating problems. One, however, stands out as most challenging of all in scope and pioneering aspect. It was presented to us by Gulf Oil Corporation. This is the story of its solution. Our directive: design a structure capable of erection in 350 feet of water, supporting drilling equipment and facilities for self-sustained multiple well drilling operations. By illustration, visualize a 40-story subterranean skyscraper rearing its one-half square block platform 6 full stories above the water. Imagine its foundation piling laid end to end, extending 8.5 miles, with conductors and bracing added, extending 25 miles. Conceive of the massive weight of 10,000 tons. Consider the potential might of the wind and sea and the obstacles they present. Then pause to absorb the significance of such gargantuan proportions. Hence, the magnitude of the task may approach comprehension. Understandably, the problems which beset us were proportionate in scope and perplexity. For instance, our derrick barge number 7, with a 250-ton capacity, the largest and most modern piece of ocean construction equipment afloat, was dwarfed by the 5,000-ton weight of each foundation unit. Bodily lifting such a huge mass to erect it was unquestionably impractical. The answer to this, as well as the multitudes of other enigma, was stubbornly pursued and overcome. Painstaking search for existing knowledge and our own development of new concepts and methods were the means of accomplishment. Substantial verification ensured the credibility of our theory. We found our primary assets to be the forces of nature herself. A preliminary report submitted to Gulf outlined the basic propositions of our design. First, design criteria were selected, which established the forces to be coped with in designing and constructing the platform. This criteria was determined with the assistance of accurate meteorology. Note, for instance, that platform deck members are specified to be 45 feet above mean still water level to place the superstructure out of the reach of the predicted hurricane wave. Another important phase of the criteria is the foundation supporting characteristic of the bottom material. Since the location for our structure is hypothetical, we have assumed a soft clay-type material similar to Mississippi Delta deposit will be encountered. This assures us a liberal cost estimate based on a worst possible condition. The second part displayed a new concept of foundation construction, minimizing need for derricks and barges. We will utilize a foundation unit's own buoyancy and the manipulation of that buoyancy to transport and erect it. Basic features of this concept are shown in these sequences. The first illustrates the towing position, with the structure stable on its bottom caissons. Floating thusly, it'll be towed to location for erection. Sequences 2 through 6 illustrate the erection operation. Progressive controlled flooding of the caissons causes the structure to rotate 90 degrees. As it approaches the vertical, it gradually settles to the bottom to attain its erected position. The various criteria of Part 1 and the concepts illustrated in Part 2 were basic requirements of a competent design. Hence, a preliminary layout was originated satisfying these prerequisites. Basically, it embraces 2 units or foundation sections, each 68 by 180 feet. When connected by field bracing, they will form a single platform, approximately 180 feet square. Thus, 32,400 square feet, or 3/4 of an acre, is provided for sustained drilling operations. This square dimension is sufficient to permit its 4 30-inch piling per leg to withstand predicted hurricane forces. Each unit is comprised of internally stiffened thin steel caissons, 10 and 12 feet in diameter, braced with steel pipe members. The 4 piling per caisson are driven through conductor pipe contained inside the caisson skin. The 12-foot caissons are sized to float the structure in its towing position with piling inserted in their conductor. Yet some 20% reserve buoyancy will remain for reasons of safety. Each outside floating caisson is compartmented so that any possible damage while in tow can be isolated. The 20% reserve buoyancy will then overcome the restricted loss. Thus, the unit will remain floating on its bottom row of caissons, an imperative requirement for towing the final location, as well as repair of the damage. The main load-bearing trusses will be a part of the jacket units. Deck beams and flooring will be unitized in sections of 180 tons and installed after the foundation is erected. One of the units, however, will contain provision in its design to vary the ultimate floor elevation in the field if necessary. This will offset any trouble encountered in accurately positioning the units at an exact common elevation. Our most repetitive habit became the inevitable compromise between pure design fundamentals and the practical demands of a unique construction technique. Following the culmination of the preliminary report and its subsequent approval by Gulf, we faced an important decision bearing on the ultimate development of the final design. Preparation of the report had indicated a basic need for substantiation of the theoretical concepts of self-flotation and erection. In addition, certain vacuum of knowledge existed which were essential to be filled in. Due to the most basic importance of these concepts, we decided to construct the model of a single unit. Fabricated of welded aluminum tubing, this 1/17th scale model duplicates dimensions and weight distribution of the proposed 40-story giant. Relative sizes of members are illustrated by noting the top main columns, 7 inches in diameter, simulating the 10-foot caissons. Corresponding 8.5-inch diameter bottom flotation members duplicate the 12-foot caissons. K-type bracing used throughout ranges from 7/8 to 1.5 inches in diameter, depicting full-size pipe members 14 inches to 24 inches actual diameter. The model is complete with a system of air-operated vent and flooding valves whose actuating air lines may be seen leading to the central control board. Depth and caisson pressure gauges constantly indicate the position of the model during the erection operations. Here in the outdoor test pond at David Taylor Model Basin, Washington, D.C., erection tests were conducted, which yielded invaluable knowledge of the structure's characteristics. Some 2 weeks of preliminary experimentation had been previously completed at our Louisiana base camp. All tests completely substantiated our theoretical procedures. The erection technique hinges upon controlled progressive flooding of the caissons. The primary means of control is the main flooding system, consisting of a valve on each caisson remotely actuated by air from a central control platform. Since closed air chambers exist above the water inside each caisson, a valuable secondary means of control lies in venting the air chambers. By means of a throttling vent valve, we can vary the air pressure in the chamber, hence controlling the rate at which water enters the main flooding valves. The rate of descent of the unit is a direct function of this flooding rate. The flooding valves in the top caissons are opened as soon as the bottom ends become partially immersed. At this point, two basic postulates govern the control operations. First, the flooding of any caisson will affect settlement. Secondly, within natural limits, speed and rotation of the structure toward a final vertical position is a function of the relative rate of flooding the top caissons compared to the lower caissons. Proper combination of these postulates is essential to this ultimate technique. Gradual revolution and descent of the model is deceiving. Dangerous changes in speed of rotation and descent would occur at various points not obvious to the viewer were not control measures taken to offset these accelerations. Erection procedure, which anticipates these critical phases, has been established by practice and experiment with the model flooding out of control. Thereby, exact rates of water and air flow through main flooding and vent valves have been precisely determined within exact time limits. Maintenance of positive stability in the unit throughout is another prerequisite. Sufficient restoring moment must exist at all times to overcome external forces of wind and wave, as well as erection stresses. This condition is inherent in a structure whenever the center of gravity is below the center of buoyancy. Almost perfect structural symmetry in the unit satisfies this stipulation, since when empty, the four centroids coincide. During erection, water flowing into the lower part of the caissons shifts the center of gravity toward the base, thereby fulfilling our requirement. It is a happy coincidence indeed that the most structurally desirable geometric shape has a physical nature satisfying our erection requirements. The construction force would consist of 4 ocean-going tugs, a derrick, and an auxiliary equipment barge containing air compressing equipment with a 3,000 cubic feet capacity. Various other supply barges would transport piling, deck sections, and bracing to the site. During erection, the structure would be oriented with its head into the sea, hanging on a yoke to a single tug. Approaching the bottom caisson valves are closed, and the top caissons are carefully flooded, effecting final revolution to the vertical. The structure is then flooded until settlement in the mud stabilizes it. Here, the first pile sections transported in their respective conductors in the caissons will be driven an initial 50 feet. Deck sections would be assembled and a crane placed thereon to expedite splicing and driving the 32 70-foot piling per unit. The second unit would then be flooded into position, the same erection procedure followed, and the field connection between the two would be completed. In salvaging the platform, the deck and superstructure units, as well as the field bracing, would first be removed. Each foundation unit would then be raised vertically clear of the bottom by air pressure ejection of water equally from each caisson. Sufficient distance would be assured to permit shooting off each pile with dynamite below the mud line without damaging the watertight caissons. The caissons are then progressively evacuated by air pressure, bringing the structure to a towing position. The only loss accruing to the operation would be the sections of piling remaining below the mud line. However, we anticipate the necessity for complete rechecking and maintenance of the units in dry dock before they are reinstalled. This accelerated action demonstrates a phenomena inherent in the physical character of the structure. Since the buoyancy is concentrated in top and bottom caissons, instability occurs when the weight distribution due to flooding completely immerses the bottom caissons and forces the waterline within the zone of the bracing members. Thus, we have seen the complete cycle of operations in erecting and salvaging the platform. It realistically demonstrates the soundness of our erection concept, manipulation by controlled buoyancy. It was imperative that we investigate the effect of various wave conditions on the structure while being erected. In the indoor towing basin at David Taylor, we selected first a 7-foot model wave as representative of possible prevalent sea conditions. The model was erected in this wave and its reactions observed. The wavelength in this, as well as other towing or erection tests, was equal to the length of the model. This length causes the most violent reaction for a constant wave height. These wave trains were generated in the main towing basin at David Taylor by a newly installed pneumatic wave machine, the largest and most accurate wave generator to be found in any model tank or basin in this country. Likewise, it is the first to be built on the pneumatic principle. An important postulate of our erection technique theorizes the ability of a sea bottom to eliminate any final oscillation of the unit, such as is seen here. In this basin, a concave concrete bottom permits no three-point support. Hence, the legs become separate fulcrum of oscillation. Our experience with erection of present type jacket foundations, however, indicates an opposite condition prevails at sea. The inherent nature of recent deposits on any sea bottom will establish by compressibility and adhesion a firm support, dampening completely wave oscillations. As the model is erected in a 25-foot seaway, note the violence of its reaction. This condition was chosen in order to determine its characteristics in an emergency situation, wherein our construction forces might be beset by a surprise squall or winds of 60 to 70 miles per hour. This test proved that the simplest practical means of protecting the structure, if surprised by a near hurricane force wind or storm, would be to sink it and leave it free to ride the storm in a vertical position. While the structure is designed to take the shock stresses of a storm, the above procedure would certainly be cheap insurance, since when sunk in a vertical position, the storm stresses are only a small fraction of those experienced while floating horizontally. The frequencies of oscillation of the model in waves can be converted to the full-size unit in a corresponding sea condition by proportion of the square root of the scale. Since the scale is 1 to 17, the frequency is over 4 times as long as the time period of the model. The dampening action as it approaches a vertical position is more apparent in this sequence than in the last. The primary purpose of our choice of David Taylor Basin was to determine the practicality of towing the structure in a seaway, to transport it thusly to the construction site. The scope of the project made this choice imperative. The size of the model necessary to test erection technique, as well as towing characteristics, eliminated consideration of other towing basins in the country located at the various universities. In addition, this research center, operated by the Bureau of Ships, United States Navy, contains the greatest wealth of experience and knowledge to be found in the field of hydrodynamics. Made available to us on a strict cost basis, this immense facility, including its 2 3/4-mile long indoor towing tanks, was a prime factor in the successful development of this project. These predicted horsepower curves were computed from test data obtained by towing the model in the slow-speed indoor towing basin. A wide range of speeds was used and various sea conditions simulated. It is the final tabulated result of our tests and will enable us to determine the towing horsepower required for any possible sea condition. You will see 4 sequences filmed of the towing tests, each in a different wave and speed condition for visual comparison of the effect. The wave condition, speed, and towing horsepower required by the full-scale structure at sea under these conditions will be indicated. In the first sequence, the required horsepower is practically negligible. The test was necessary, however, in order to determine the shape of the horsepower versus speed curve. A comparison of the required towing horsepower at a similar speed for both wave conditions will indicate the tremendous effect of the waves on the towing resistance. This effect is much greater on this structure than on a standard ship hull. It's due to the increased component of wave resistance caused by the multitude of immersed bracing members. Many tests were made in order to catalog other characteristics of the structure under varied conditions, which cannot be shown here due to time limitations. However, those concerned with this project were continually amazed by the unpredictable and at times unexplainable actions and results. The towing tests substantiated our original theory that a symmetrical structure would be extremely stable in tow. The results were even more satisfactory than we had hoped for. The symmetrical resistance of the immersed bracing members actually creates a tremendous restoring moment to any attempt to pull or thrust the structure from the line of tow. The violent pitch in this situation actually demonstrates an amplitude of 30 feet for the full-scale unit. It's probable that in a sea condition such as this, the towing speed would be cut to about 2.5 knots, depending on the current velocity and the amount of tug horsepower assigned to the construction force. And so we have followed the development of an embryonic concept as it matures into a practical design reality. Intelligent appraisal indicates the lower limit of its practicality to be within the 125 to 150 foot depth range for normal Gulf of Mexico locations. On the other hand, the extreme depth limit is for the present unknown. By virtue of these invaluable model tests, we have proven conclusively the soundness and practicality of our towing theories and erection method. Filling in this vacuum of knowledge permitted completion of the multitudes of design details hinging upon definitive techniques. We can now say to you with full confidence, it can be done. Our appreciation must be extended to the engineers and technicians at David Taylor for their competent guidance and counsel, as well as the members of the Gulf Offshore Committee, under whose able direction this project has progressed. And to the management of Gulf, we extend our humble appreciation for your expression of confidence in assigning to us the development of this pioneering effort. Through your vision and foresight, a major contribution has been made to your industry's march of progress in the further unknown frontiers of oil exploration.